Okay, Chemistry 3101. Let's talk about the reduction of an alkyne. And we're going to talk about hydrogenation. And we're also going to talk about a different type of reduction. But the bottom line is we're going to look at three types of reduction. We're going to look at taking an alkyne like this, and we're going to look at reducing it all the way to an alkane. Then we're going to talk about reduction to make a cis alkene. And then we're also going to take a look at a reduction to make a trans alkene. So we're going to look at all of these different types of reductions, but we're starting out with the same old catalytic reduction or hydrogenation that we saw in chapter 8, where we just used hydrogen and platinum, palladium, or nickel, and that reduces all the way down to an alkane. So the same thing will occur with an alkyne. If you take an alkyne like, so this is 2-butyne here, and you subject it to hydrogen gas and platinum, it reduces it all the way down to the alkene. So you go from an alkyne to an alkane when we treat with hydrogen and palladium, platinum, or nickel. Now, it turns out that the first addition, okay, because you add 2 moles, right, for every 1 mole of this, you need 2 moles of hydrogen. Well, it turns out that the first mole, right, this is the first mole, this is the second mole here. The first mole actually does add via a syn addition to make a cis alkene, okay? So what the what the next concept we're going to look at is there a way to stop here? Could we stop here so that we could just make a cis alkene? And the answer is yes, we can do that. So what we use is what's called a deactivated or a poisoned catalyst. They both mean the exact same thing. And what it does is it stops the hydrogenation at the cis alkene and it doesn't keep going. Now, if you're wondering, what are these deactivated or what is a deactivated or poisoned catalyst? Well, there's actually a few of them out there. One of them is Lindlar's catalyst. Okay, so Lindlar's catalyst, that's usually what my students write. Okay, sometimes they'll write poison catalyst. I would accept that. That's totally fine. Sometimes they write Lindlar's catalyst. I would totally accept that. And like I was telling my students before I started recording this video, I was looking at MCAT and DAT review materials, and sometimes they use the P2 complex. So they'll actually just write P2 or this dinickel boron complex here. And I will accept that as well. Any of those are totally fine. But if you're wondering what Lindlar's catalyst is, well, you don't have to memorize the structures. This big, quinoline with palladium and barium sulfate, blah, blah, blah. Anyhow, you don't need to know all that. All you have to know is that the poison catalyst stops the hydrogenation at the cis alkene. Now, if you look at the reaction coordinate diagram, right, the potential energy for the hydrogenation reaction without a catalyst is actually, it's really high. So you see there's a huge activation energy to do a hydrogenation without a catalyst. But it turns out that the catalyst, the poison catalyst, Lindlar's catalyst, the P2 catalyst, the only thing it does is catalyzes the first addition, okay? Only that one. It doesn't do anything in the second step. And so it stops at the cis alkene. And you can see that it goes by an alternate pathway as well. And we don't discuss that mechanism in this class. So again, Lindlar's, poison catalyst, P2, they all mean the same thing. And you can put any single one that you want. Okay, so now we've talked about how to reduce all the way to an alkane and how to make a cis alkene. Well, the next one is what we call a dissolving metal reduction. What that does is it takes your alkyne and it converts it to a trans alkene. So a cis, we used poison catalyst, but to make a trans alkene, we use dissolving metal reduction. And you can see that you actually put pure sodium in the reaction. And you guys know that sodium is a metal. It can be dangerous, right? If it's put in water, it can cause a fire or an explosion. But anyhow, what we do is we put sodium in liquid ammonia, which doesn't cause any kind of problem. But everybody should know that sodium has 1 valence electron, right? It's in group 1. And so that metal, sodium, is able to give up an electron, and via a radical mechanism that you don't have to know how to draw in this class because we haven't covered radicals yet. Okay, we will cover it in the next chapter. We end up with an intermediate along the way that's called a radical anion. So I'm going to put here radical anion along the way, and then we end up going to the trans alkene. So let's talk about what a radical anion is. So it says here, the transalkene is produced due to the fact that the reduction occurs via a radical anion intermediate. Again, I'm not going to ask you to draw a mechanism of this or anything, but you should have an idea of what a radical anion is. What a radical anion is this. It's like you have a carbon-carbon double bond, and on one of them you have a radical, which is an unpaired electron, and on the other one you have an anion. So that means I have high electron density on this carbon and high electron density on this carbon. So what are they going to want to do? They're going to want to get as far away from each other as possible. Sorry, there's a plane going over my house. Okay, so they were going to want to get as far away from each other as possible to avoid the repulsion of the two like charges being near each other. And so when we have the radical anion, so again, this is the radical anion, they get as far away from each other as possible. And that is why we go from here to the trans, we get the trans alkene. All right. So it says here, look over mechanism 9.1. You don't have to memorize it because we're going to go over radicals in more detail in chapter 10. So what's the conclusion? Is if we take an alkyne and we treat it with just hydrogen, palladium, platinum, or nickel, we go all the way down to the alkane. If we treat it with Lindlar's catalyst, which is the poison catalyst, or you could write P2 catalyst, we end up with a cis alkene, okay, with Lindlar's catalyst. And if we use dissolving metal reduction, so that's sodium and liquid ammonia, we end up with the trans alkene, and that proceeds through the radical anion, okay, to give us the transalkene. Again, there's a mechanism shown in the textbook, but we don't cover radicals until chapter 10. Now, of course, the cis and the transalkene, you guys know from chapter 8 that you can just reduce that all the way down, whether it's cis or trans, to an alkane. So now, yeah, so there you go. So that covers the reduction of alkynes. That's the whole thing right there. So let me just find my notes here. And now what we're going to do is we're going to take a look at a question, and this is not meant to be a mind boggler or anything. Sorry, just closing the window there. Does anybody else hear airplanes outside? Is it just me? Okay, there's a couple of us that are hearing them. Anyway, sorry about that. All right, so the first one, we're taking diisopropyl acetylene. If we want to make a cis alkene, what are we going to do? We're going to use hydrogen gas. So we just write H2. And if you want to put gas, that's fine. You don't have to. And then we'll put Lindlar's catalyst. Okay, and if you want to write poison catalyst, that works too. The next one, we want to make the transalkene. So we're going to use dissolving metal reduction. So that's sodium and liquid ammonia. Same thing with the next one. We're taking, what is it, 2-pentyne, and we want to make trans 2-pentene. So we want to make a trans compound like we did before. And so we're going to use dissolving metal reduction, so sodium and liquid ammonia. So again, we get a trans compound. For the first one, we get a cis compound. And the last one is we're just hydrogenating all the way down to the alkane. So for that, we'll use hydrogen and platinum. All right, there you go. So that covers all of the reduction of alkynes. So now you know how to reduce an alkyne down to an alkane. You know how to make a transalkene and a cisalkene. All right. So now that we've covered that, let's talk about hydrohalogenation of an alkyne. And you guys remember hydrohalogenation is adding a hydrogen and a halogen, so HX. And you guys remember Markovnikov and anti-Markovnikov addition, I'm sure. Very, very well. So it turns out that hydrohalogenation affords Markovnikov addition as well when we add across an alkyne, just the same way as it did with an alkene. So check it out. If we do addition to an alkene, this was covered in chapter 8. You guys know that you proceed through the most stable carbocation. You could put in here the rich get richer, right? That's kind of the mnemonic that we used for Markovnikov addition. of HX, whether it's HCl, HBr, or HI, across a double bond. But with an alkyne, so now we're in chapter 9, we see it follows the same rationale. So if we used 1 mole of our alkyne and 1 mole of HX, we're going to get a Markovnikov addition like this. All right. So if you use excess HX, it's the same thing. You end up with a geminal dihalide, right? It's 2 successive Markovnikov additions. Well, it turns out that you don't need to know the mechanism for that reaction. So if we go here, it's not just a simple reaction. So no need, I'll put no need for mechanism. Okay, and the textbook goes into a little bit of detail on that as to the rationale as to why you do not need to know the mechanism, but it's because it's actually a termolecular mechanism. So you guys remember first order and second order? It's actually third order mechanism. And the reason it is a termolecular mechanism is because that way you avoid forming an allylic carbocation, or sorry, a vinylic carbocation like this. So that is a big no-no in organic chemistry. So again, just the take-home message is it's a Markovnikov addition, and you won't be asked to draw a mechanism. However, if you guys remember anti-Markovnikov addition of HBr with peroxides, that's going to work in the same fashion as it did with an alkene, except now you're going to get a mixture of cis and trans or E and Z compounds. All right. Now, this mechanism, again, is going to be covered in chapter 10, so there's no need to know the mechanism here. But something I want to point out is some students have been asking me, like, is this an E compound or is this a trans compound? The answer is when you have 2 groups that are identical, right? Like in this compound, you see you have a hydrogen here, you have a hydrogen here. You could call this a trans compound. It's totally fine to call it that, but you could call it E as well. Either one is technically correct, okay? There's not one that's more correct than the other. We can always use E and Z for alkenes, but we can't always use cis and trans, because to use cis or trans, you have to have groups that are identical. But again, either one is acceptable. Same thing here. You could call this a cis compound or a Z compound. They are both totally fine. So there we go. So that's a little bit about hydrohalogenation. And so now talking about making a dihalide, well, if you do your double Markovnikov addition with HX, whatever it is, okay, now you could do a double elimination. I don't know why you would want to do this and then do this. That seems like a little bit ridiculous, but it's just for instructional purposes here, right? He's showing you that if you take an alkyne and do a double hydrohalogenation, you end up with a geminal. So this is a geminal dihalide. And then, of course, if you did a double elimination, deprotonation, and then protonation, you'd end up with a terminal alkyne. Anyhow, just kind of showing you how this all goes together. Okay, so with that in mind, let's see if we can solve these problems here. And again, they're not meant to be confusing or anything. It's just to sort of flesh out the idea a little bit more. So we're starting out with this geminal dihalide, and it says predict the major products expected for each one of the following reactions. Well, we have a geminal dihalide, and first we're treating it with excess sodium amide, followed by water. And so what that's going to do is that's going to make the carbon-carbon triple bond, right? There's a carbon here and a carbon here. And so we're going to form the triple bond like this. Okay, that's going to be after the first step. But in the second step, we get an anti-Markovnikov addition of HBr. So it's not the rich getting richer. It's the other way around. So we're going to end up with both the E and the Z alkene. So we're going to end up with, come on, pen. We're going to end up with the E alkene like this, and we're also going to end up with the Z alkene like that. Okay, so we end up with a mixture in that particular case. The next one, in the first 2 steps, you can see what's going on because it's the exact same thing we did in the last one. So we'll draw our, what we'd call this phenylacetylene, I guess. So we'll take phenylacetylene. And then it says we're treating it with excess HBr. Remember, this is going to be Markovnikov addition, right? This one here was anti-Markovnikov addition. And if it's excess, we're going to make the geminal dihalide. And so after that step, we're going to end up with just one compound, which is this compound here. And there you have it, my friends. All right, give me a thumb. Is everybody with me on that? Thumbs up on those concepts. So first we covered reduction, then we went into hydrohalogenation. We talked about Markovnikov. I said there's no mechanism that you have to know for Markovnikov or anti-Markovnikov. So I'll write that down on this slide just so you're fully aware, okay? No mechanisms. Okay, we're going to look at this mechanism a little bit in chapter 10, but for this chapter, for quiz 9, you don't have to know any of the mechanisms. Okay, so now that we've covered Markovnikov addition of a halo acid like HBr, HCl, HI, then we talked about anti-Markovnikov addition of HBr. Well, let's talk about hydration, right? Because we talked about Markovnikov addition of water across a double bond, and we talked about anti-Markovnikov addition of water across a double bond. So with that in mind, let's take a look at hydration. And it starts right here. Okay. All right. So hydration. Well, it turns out that we can do a Markovnikov addition of water and an anti-Markovnikov addition of water across an alkyne. So it says here, alkynes can also undergo Markovnikov hydration. Okay. The process is generally catalyzed with mercury 2 sulfate. So if we have HgSO4, you can call this mercuric. So mercuric sulfate, or you could call it mercury 2 sulfate. Okay, either one is fine. Okay, so you take your sulfuric acid and water, right, which together, those two, when you mix them together, they make hydronium ions, but you need the mercuric sulfate or the mercury 2 sulfate. Now, why would that be? You can't just draw a mechanism. So if you're wondering, why can't I just draw a mechanism where I show the rich getting richer? So let's say I draw, my H3O plus. I'll just make a shorter version of the mechanism. And don't write this down because it's a heresy. But let's say you tried to draw a mechanism like this. Okay, you'd end up with something like this. So you'd end up with a vinylic carbocation. That is a huge, huge, huge no in organic chemistry. So that doesn't happen. Okay, none of this, what I just drew, none of this is going to happen. So let's pretend it didn't happen, okay? Because vinylic carbocations are so unstable. And so the mercury 2 sulfate is what stabilizes the molecule along the way. And it's actually what promotes the reaction, okay? There's no details of the mechanism provided in our textbook, but that's what the mercury 2 sulfate is for. So you still follow the rules. The rich get richer, okay? So you still follow the rich get richer, but when you draw the product, what do you end up with? Now you have 2 protons here, and you have the hydroxyl here. So you see that that's an enol, and we know that enols are not stable. They undergo tautomerization, and this one is going to undergo tautomerization to give us a ketone. More specifically, this is what we would call a methyl ketone, right? Because we have a methyl group here. So we call that a methyl ketone. All right. So that's Markovnikov addition of water, is we need sulfuric acid and water and mercuric sulfate to promote the reaction. So you need to know the mechanism of tautomerization. This is one that everybody expects their students to know, okay, is the mechanism of keto-enol tautomerization. So it's just a proton transfer to make this carbocation, which is resonance stabilized. You draw the oxonium. This, what I have in the red circle, is going to contribute more to the resonance hybrid because both the carbon and the oxygen have a complete octet. That's an oxonium ion. It undergoes a deprotonation, and you end up with your ketone. So remember that an enol and a ketone, those are tautomers of one another. And tautomers are they're nothing more than isomers that differ in the placement of a pi bond and a hydrogen. Okay, that's all they are. Tautomers are isomers that differ in the placement of a pi bond and a hydrogen. And you see that here The only difference is the pi bond went from here to here, and the hydrogen went from here to over here. Okay, so that's what tautomers are. Now, what about if you have if you have an internal alkyne? Well, there's no hydrogen attached to this carbon, and there's no hydrogen attached to this carbon, so there's no such thing as Markov-Nikov addition, right? We could say here Markov-Nikov does not apply in this specific case. And so that case, you're going to end up with the carbonyl on either one of those carbons. And so you're going to end up with a mixture. Okay? You end up with a mixture this way. And there's nothing you can do. You can't avoid getting a mixture. You just end up with a mixture, and maybe you could separate them, maybe not. I guess it depends on the situation. But anyhow, so question 9.18 says, draw the major products expected when the following alkyne is treated with aqueous acid in the presence of mercuric sulfate. So what they're asking us to do is draw the product that would be formed if you mix some sulfuric acid, water, and some mercury 2 sulfate and subjected this terminal alkyne, so this is terbutylacetylene, to these conditions. Well, we're going to follow the rules. The rich get richer, and so you'd actually end up with this enol, but we know that this enol is not stable. It's going to undergo tautomerization to give us a methyl ketone. All right, the carbonyl is more stable. The carbonyl compound is more stable than the enol. So remember, the enol undergoes tautomerization to give us the ketone. All right, and more specifically, again, this is a methyl ketone that we get. Now, the next one says identify the alkyne that you would use to prepare each of the following ketones via an acid catalyzed hydration. Well, you can see that in the first one, we have our methyl ketone right here. So this is where the triple bond is going to be, is right there, and we're just going to do a Markov-Nikov addition. So our starting material is going to look like this. So 1, 2, there we go. Something like that, and then all we have to do is treat it with sulfuric acid and water and mercury 2 sulfate, and that's going to give us, let's draw the enol. We're going to follow the rule, the rich get richer. So there's our enol, and then that is going to tautomerize. So we'll put here tautomerize to give us the product. The next one is a little bit trickier because you see that this is internal, right? We don't have a methyl ketone. We have an ethyl group on one side of the carbonyl and a propyl group on the other. So there's actually two possibilities here. You could have the triple bond coming from here. So in that case, you'd end up with this alkyne, okay, in our retrosynthesis. Or if you had the triple bond here, then it would come from this alkyne. So this one. Here we go. So which one of these is going to be correct? Because there's only one correct answer here. Well, if with the first one, okay, if we have this carbon in red and this carbon in blue, if the carbonyl goes on the carbon in red, okay, let's say I treat this with the conditions, I'm going to end up with this ketone. I'm going to end up with, I'm going to end up with this ketone. If it goes on the carbon in blue, then I'm going to end up with this compound, which is the desired compound. Come on. 2, 3, like that. Okay, so I end up with some of the desired compound, but I also end up with some of this other isomer, okay, which I don't want. Now, if I use the compound in blue, the alkyne in blue, I should say, and I treat that with mercuric sulfate, okay, it wouldn't matter if it went here or here. I'm going to end up with the same compound both times, or either way. So when I use my sulfuric acid, water, and mercury 2 sulfate, the only possible compound I could isolate in this case would be the desired product. And so this is going to be the way that we make the compound, right? Because we don't end up with a mixture. We only end up with one compound. Give me a thumbs up if that makes some sense. Okay, so from the last slide, so if we're starting out with this terminal alkyne here, we're treating it with sulfuric acid, water, and mercuric sulfate, right? We follow the rule, the rich get richer. We can put in here, the rich get richer. Okay, this carbon is the one that has the hydrogen. So now it has a total of 2 hydrogens, and it also has the hydroxyl, but that's an enol, and then it undergoes tautomerization to give us the methyl ketone. Does that help a little bit? Okay, cool. Awesome. All right, let's move on from there. So we've talked about Markovnikov addition of water across a triple bond. So now we're going to get into anti-Markovnikov addition of water across a triple bond. So you guys remember hydroboration oxidation for an alkene. So that was borane and THF followed by hydrogen peroxide and sodium hydroxide. So now we follow anti-Markovnikov rules. And so this carbon has a hydrogen on it. So now instead of taking the proton, that one takes the hydroxyl, and the other carbon, meaning this one here, takes the hydrogen. Okay, so we end up with an enol, and that enol undergoes tautomerization to give us what? An aldehyde. So when we do the anti-Markovnikov addition of water across a terminal alkyne, we get an aldehyde. Now, a little bit on base catalyzed tautomerization, because remember the tautomerization in Markovnikov addition was acid catalyzed. This one is base catalyzed, and we expect you to know the mechanism of both, of acid catalyzed tautomerization or base catalyzed tautomerization. Well, the mechanism isn't much of a stretch, really, because all it involves is a proton transfer to make what we call an enolate. Then we have these 2 resonance forms here. You draw the carbanion that I have in the blue circle, and it does a proton transfer, and you get your aldehyde. So keep in mind that this enolate, where does the name come from? Well, you know that 8 in organic chemistry, or chemistry in general, means negative charge, right? Sulfate, nitrate, carbonate, okay, enolate. So it's got a negative charge, and it is an enol, right? You have the ene for the ene, and then you have the all, right? Because this is, once it's protonated, it becomes an alcohol. So that's where the word enolate comes from. Enolates are actually covered in gross and gory detail in chapter 21 of the textbook. So if you're taking organic chemistry 2 next semester, be sure to look forward to that. A whole chapter almost about enolates. All right. Now, as far as the hydroboration oxidation goes with a terminal alkyne, it says if you use borane, it can undergo 2 successive additions. And when it does that, you end up with an undesired product. Okay, I'm not going to go into all the details on this. I'll kind of put this as an FYI almost in a way. But the rationale is, the kind of the conclusion that we draw is using borane is not good. Okay, we don't want to use borane because it keeps adding over and over, and we don't want that to happen. So what we do, instead of using BH3, so instead of using BH3, so out with the old, in with the new. So we use BH, and then we have some kind of alkyl group attached to it. So R2BH instead. Now, the reason why we replace 2 of the hydrogens with alkyl groups is so that it can only add once. Now, what are these alkyl groups? Well, you can see that one of them is in this bicyclic compound. We call this 9-BBN, which is 9-boron bicyclo 331 nonane. You don't have to know how to name this. Usually my students will just write 9-BBN. Okay, so this is 9-BB. 9-BBN, okay, and it's totally fine to just write that one. Dicyamylborane is shown in here as well. I can tell you, I've been teaching this class for a long time, and I don't remember the last time a student brought up dicyamylborane, but I will add this because I have a few students who are interested in things like MCAT or DAT. And I've also noticed that it's in the ACS, but it's funny because it's not in our textbook anywhere. But there's also kind of a generic form of both of these that we use sometimes. And you might think it's kind of goofy, but what we do is we draw something like this, okay? So this means there's like a bicyclic ring attached to the boron, and then we put the hydrogen like that, okay? Also totally acceptable. Yeah. He might have been. You never know. All right. So there you go. So there you go. So that's another way that we write a borane. This is something like that. So the modified borane allows reagent allows the conversion of the terminal alkyne into the corresponding aldehyde. So of course it passes through the enol. So remember, this is anti-Markovnikov addition. So our enol would be this, right? And then it undergoes tautomerization in base to give you the aldehyde. So the enol is not captured. Okay, it's just an intermediate along the way, and then it undergoes tautomerization. Now, like I told you, instead of writing dicyamylborane, my students, again, will almost always just write 9-BBN, and I don't blame them. It's easy to remember. It's very distinct, so they jogs your memory a little bit faster than saying dicyamylborane. So what's the conclusion that we can draw from section 9.7, right? We talked about both Markovnikov and anti-Markovnikov addition of water across a triple bond. We'll check it out. Here we go. So here's the conclusion of section 9.7. If you have a terminal alkyne, right, an alkyne that has a hydrogen on one of the carbons, okay? If you use sulfuric acid and water with mercuric sulfate, you do a Markovnikov addition, which would give you this enol in this case, and then that's going to undergo tautomerization to give you a methyl ketone. If you use a hindered borane, so again, 9-BBN, you could write that, or you can put R2BH, or you could put something like this, okay, the bridged bicyclic, they all mean the same, or you can write dicyamylborane, that's fine as well, okay? What that's going to do is an anti-Markovnikov addition to produce this kind of enol, which is going to undergo tautomerization to give you an aldehyde. Now, this isn't fodder for this section, but ketones and aldehydes come up a lot in chemistry 3111. In fact, there's a whole chapter on them. If you want to take a look, it's chapter 19 in your textbook. The entire chapter is about aldehydes and ketones. I mean it. Nothing else is in there, okay? And they even show up in chapter 12, which is the first chapter of new material that's covered in organic chemistry too. So ketones and aldehydes, very, very important. So you can imagine that these reactions are going to show up in organic chemistry too quite a bit because we need them. All right, so let's take a look at these. You see the first one, you take a terminal alkyne, you get a methyl ketone. The second one, you take a terminal alkyne and you get an aldehyde. So what are the conditions? Well, if we want to make the methyl ketone, we would have to do a Markovnikov addition in that case. And so we would end up with this enol. So this enol, which is going to undergo tautomerization. But to do the Markovnikov addition, what do we need? We need sulfuric acid, water, and we need our mercury 2 sulfate. And that's what promotes the reaction or lowers the activation energy. And the next one, if you want to make the aldehyde, well, that's going to proceed through this enol. So I'll practice drawing my enols here. There we go. So that's just the intermediate. And again, that's going to undergo tautomerization to give you the aldehyde. For that, we need 2 steps. We need, let's try 9-BBN in the first step. And the second step is the same old H2O2 and sodium hydroxide that we saw in anti-Markovnikov addition of water across a double bond. All right, so that's a little bit about hydrohalogenation and hydration. So we've covered both of those. We talked about Markovnikov addition and anti-Markovnikov addition. And that brings us to halogenation. You guys remember talking about the halogenation of an alkyne or of an alkene, where we said, let's say you have, some kind of double bond like this, and then you treat it with bromine like that. You end up with an anti-addition where one bromine is going to be up and the other bromine is going to be down. And then, of course, you end up with the enantiomer. So that's what we covered in chapter 8. Okay. But what we're going to see here is that if you take an alkyne and you treat it with excess halogen, and this halogen has to be Cl2 or Br2. You can see that right here. Fluorination is too violent and iodination is too slow. But what you do is you add halogens on everything. So you end up with a tetrahalide. Now, there's no mechanism provided in the textbook for this, so you don't have to do it. But notice that when it's excess of your halogen, you get a tetrahalide. So you might be wondering, well, what would happen if I just added one equivalent? And it's a good question. And if you add one equivalent of your halogen, so what that would mean is if you had 1 mole of this, you'd add 1 mole of your halogen. You actually end up with a mixture of the trans and the cis, okay? With the trans or the E product, so this is trans or E as being the major product because it's less sterically hindered. But check this out. These are the words of the author of the textbook, okay? This is not Mr. Dion. Before sometimes as scientists, we think we've got it all figured out. But if human history has proven something, it's that we certainly don't. And it says here, at least he has the hubris to admit the mechanism is not fully understood. Okay, you see the words right here, not fully understood. So there are some mechanisms that we have an idea about. There's some that we understand very well, but there's others that we know what we're going to get, and we're not sure exactly why. Okay, and I've probably told you this before that I have a book in my office. It's not mine; it's my office mate's, but it's called The Art of Drawing Reasonable Mechanisms in Organic Chemistry. Anyhow, I always giggle at that book whenever I look at the title. But anyhow, so let's move on from there. So we've covered section 9.7 and 9.8. Let's get into 9.9, which deals with ozonolysis. And I know you know this, ozonolysis of an alkene. If I just rehash just kind of the memory of ozonolysis from chapter 8, what was it? First step was ozone, second step was DMS. Right, and in that case, you'd end up with this, times 2, of course. So that was ozonolysis of an alkene. Ozonolysis of an alkyne is different. 2 things. The main thing is that the second step is not DMS; it's water in the second step. So you can't use that the zinc either. That doesn't work. You've got to use water in the second step. But instead of getting an aldehyde or a ketone, you end up with a carboxylic acid if you have an internal alkyne. Okay, so you cut it right down here, and it's almost like your triple bond. You kind of spread it open, then you're like 1 oxygen here, 1 oxygen there, right? So you end up with 2 carboxylic acids. But if you have a terminal alkyne, from the side that has the R group, there's my green pen, from the side that has the R group, you're going to get a carboxylic acid from that. But from the side that has the hydrogen, that actually gives you CO2. Okay, so you end up with CO2, which is a gas. Okay, so that goes up in the smokestack. So this is definitely an irreversible reaction. There's no mechanism provided for this. Okay, none, no mechanism. In fact, you've probably noticed this already. There's actually very few mechanisms in this chapter, very few compared to the other chapters. So it says here, predict the products of the ozonolysis of this compound. So this would be what? Dicyclopentyl acetylene, you could call this. First step ozone, second step water. So what we're going to do is we're going to cut right down the middle like this, and we're going to end up with 2 moles, or 2 equivalents, we should say, of the carboxylic acid. So this compound would be called, believe it or not, it's called cyclopentane carboxylic acid is the name of the compound. Give me a thumbs up if you're with me on that. Again, no mechanism required for this one. Everybody with me on the idea of ozonolysis of an alkyne? Is anyone? There we go. All right. So I'll write here for you. No mechanism for this guy. Okay. So don't even worry about a mechanism for that reaction. So there you go. So you probably noticed, like, hey, look, Mr. Dion, I started with 1 mole of this and I get 2 moles of this. It's like putting a quarter in a slot machine and pulling out 50 cents. Kind of, in a way. So if you wanted to make a carboxylic acid, and if you could have the precursor alkyne, okay, especially if it's symmetrical, or I mean, if it's symmetrical, you take 1 mole of whatever you're starting with and you double it. So you end up with twice as many moles of the compound. So that's kind of a cool thing. Anyhow, I've never used this reaction in my own personal life. Never had to, but it is pretty cool. Anyhow, let's take a look at a neat reaction here. It just says, what's the ozonolysis product you would get when you take this giant ring? How many carbons are in this thing? There's 11 carbons. If you remember at the beginning of the lecture, I told you that cyclononine, so this would be cycloundecyne is what you would call this. Cycloundecyne. Okay. So this compound obviously is stable, or they wouldn't have put it in here. So it shows you how big a ring you have to have before you can incorporate a triple bond in there. Anyhow, so if we were to take this compound and if we treated it with step 1, ozone, step 2, not DMS, but water, what are we going to do? We're going to cleave right here. And you can see we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbon. So look, we're going to do this. When my pen touches the paper, that's carbon 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Like that. We put a carboxyl group here. We put a carboxyl group here. And just like that, we're done. So this would be called undecane dioic acid is what you would call this compound. You don't have to name it, but is everybody with me? Who thinks they could get this one? Give me a thumbs up if you're like, I could solve this. I knew you. Awesome. I know you can. Okay. Trust me. If I have faith in, I have a lot of faith in my students. They're amazing. Okay. So there we go. So that's a little bit about ozonolysis. So I think it's time for us to take a break. Not because I've been lecturing for so long, but I would like to split up the videos a little bit because alkylation of terminal alkynes is something completely different, and it shows us how to make carbon-carbon bonds. But before I turn the video off, I want to show you that we're very close to the end of the chapter, but I do think it's an appropriate time to stop because if you look at the reactions of alkynes summary, okay, what are the things we've covered up to this point? We've covered the double elimination of a geminal dihalide. We've covered the double elimination of a vicinal dihalide. We covered Markovnikov addition, right? Hydrohalogenation with excess or with one equivalent of HX, okay? We've covered hydrogenation with Lindlar's catalyst. We've covered hydrogenation with a platinum catalyst to an alkane. We've covered sodium metal reduction. We covered Markovnikov addition of water. We covered anti-Markovnikov addition of water. We covered halogenation, whether it's one equivalent or excess. And we've also covered ozonolysis. So we've literally covered all of these reactions, but hold the phone. We are not done, my friends, okay? In fact, I'm really not grasping at straws, but I'm taking a chance here. If I say we haven't covered the most important reaction in the chapter. Now, all of these are extremely important, but something we haven't looked at yet is how to make a carbon-carbon bond with a terminal alkyne. So that's why I want to take a break here, because that's going to be the next section, is deprotonating our alkyne and then making a carbon-carbon bond. And I don't know if I've told you, what's the surefire way to win a Nobel Prize in organic chemistry is to find a way to make new carbon-carbon bonds. So it's a very important section.